How do we capture the brain's language in Neurotech? Have you ever wondered how we can translate what the brain is saying? Capturing the brain's language in neurotechnology is a fascinating process that involves understanding how our brains process language. This begins with the concept of data acquisition, where we record and interpret brain activity related to language, whether it is spoken or imagined. To capture these signals, we use various techniques. One common method is functional magnetic resonance imaging, which measures changes in blood oxygen levels in the brain. This technique gives us a good view of which areas are active during language tasks. However, it does have a slower response time compared to other methods. Another popular approach is electroencephalography, which records electrical activity from the brain's surface. It allows us to see rapid changes in brain activity, making it useful for understanding how we process speech. Magnetoencephalography is similar to electroencephalography but measures magnetic fields instead. Both of these methods provide real-time data but have less spatial accuracy than functional magnetic resonance imaging. Once we have gathered this data, we move on to decoding the signals. This is where machine learning comes into play. Advanced models, including deep learning architectures, are trained to recognize patterns in brain activity. These models learn to connect specific brain signals to words or phrases. For instance, they can translate what someone is hearing or even what they are imagining saying. Different brain regions are involved in this process. Some areas focus on understanding the meaning of words and sentences, while others are linked to speech production. By targeting these regions, we can decode not just the sounds but also the concepts behind them. Training these models requires extensive data. Participants often listen to or think about language while their brain activity is recorded. This helps the system learn individual patterns, making it possible to decode new language content that the model has not seen before. In practical applications, this technology is particularly helpful for individuals with speech impairments. Brain-computer interfaces can restore communication for those who cannot speak. Non-invasive methods are especially promising since they do not involve surgical risks and can be adapted for everyday use. In summary, capturing the brain's language involves recording brain activity related to language using techniques like functional magnetic resonance imaging, electroencephalography, or magnetoencephalography. Machine learning models then decode these signals into words and concepts. By focusing on specific brain regions and training on individual data, we can create systems that translate thoughts into text or speech, opening new avenues for communication.